This is a good time to point out that you are entitled to a limited number of retakes on the quizzes. Unlike some courses you may have taken from other people where the instructor says, well, I dropped the lowest grade, or I dropped someone particularly generous, maybe drops the lowest 2 grades. Not so generous. I don't get rid of your bad grades for you. Rather, I give you the opportunity to get rid of them yourself. So here in the back of my notebook, I have another quiz out of the same homework assignment. And if you want to take that one, better of the 2 grades counts. So I'll get this back to you the next time we see each other, which, see, it's Wednesday, so I guess that won't be until Monday, actually. But you should probably have a halfway decent idea how you did at this point. But anyhow, if you get your paper back and there's a big red 6 on the top, if you take it over again and get a 9, the 6 just disappears and your grade on this quiz is now a 9. If you take it over and get a 4, well, you get to keep the 6. You have nothing to lose except that I only allow a limited number of retests, 5 of them. There are 14 quizzes in the entire course, and anybody who isn't just using it to procrastinate probably doesn't need more than 5 retakes. In a typical class, there's usually only a couple of people. Actually, there's only 8 people here. Maybe only 1 or maybe 2 people will max out by the time the course is over. The deadline is 1 week, okay? Sometimes people want to take it over immediately. They'll say, can I take it again during the break? The answer is yes. So, it's fresh in their minds. More often people want to go back and study some more, which may be a good idea in some cases. The other end of the window is a week. So when I go home next Wednesday is the latest time you can take it over, and any time in between that you can catch me, whatever works best for you. So that's the story on that. Time for some more notes. Section 2. Electric potential. So in section 1, I introduced the idea of an electric field vector as this is a way of describing the strength of the field. A strong field will exert large forces on charges that you put in it. A weak field will exert a weaker force on any charge you might put in it. But the force on a charge depends not only on the strength of the field you've placed it in, it also depends on how big of a charge it is. The force per unit charge is something that's a property of the field only. Twice as much charge would feel twice as much force, same ratio. So that's one way to describe the field. Electric potential is another way of describing the field, this time in terms of energy rather than in terms of forces. And for those of you who took the first part of the course, the section on mechanics, you saw there that there are different ways of looking at the world. Sometimes it's more convenient to think of things in terms of work and energy. Sometimes it's more convenient to look at things in terms of forces and Newton's laws. If I give you some problem where there's a box sliding down a frictionless ramp and you're supposed to figure out how fast it's going at the bottom, one way to do it is you can draw the free body diagram and get all the components of the forces, put that into F equals ma. That'll tell you the acceleration. From the acceleration, you can get the final velocity. Or what's probably a little easier for that particular problem is conservation of energy. Potential energy in the beginning equals kinetic energy in the end. mgh equals 1/2 mv squared. Solve for V final. And some other problem, the F equals ma approach might be more straightforward. So sometimes Thinking of forces is a good alternative. Sometimes thinking in terms of work and energy is the more convenient way to go. But I should redefine some of the words here because not everybody necessarily took something equivalent to Physics 121. It's not officially a prerequisite for this course. So energy means the ability to do work. Let's start with what the word work means. Basically, if I go pushing a book across the counter there, the amount of work I did is how hard I pushed times how far I pushed. Newtons times meters. This assumes that the direction I'm pushing is parallel to the direction it moves. Things can get a little more complicated than that, but yeah, let's avoid that issue. I already covered that last fall, and I don't really want to do that whole course over again in this course. So up there it was a piano, not a book. You push the piano a distance delta x using a force F, and the work is F times delta x. Work in the SI system is measured in a unit called a joule, which is a Newton times a meter. Force in newtons, distance in meters, force times distance is work. Anything which is capable of doing work possesses energy. This is what the word energy means. There are a number of different ways that something might be capable of doing work. Kinetic energy is the work that something could do because of the fact it's in motion. I think the example I started with last fall is you've got a hammer moving at about 40 miles an hour as it approaches a nail. It's going to exert a force on the nail as the nail moves through some distance. So the moving hammer is capable of doing work. The thing that makes it capable of doing work is the fact that it's in motion. The energy of something's motion is kinetic energy. Chemical energy, a substance like gasoline is capable of doing work because of a chemical reaction it can undergo. If you put the gasoline in an engine, it can make your car go down the road. Heat. You can build a fire under a steam engine, and that'll make some vehicle move. Force times distance, it's capable of doing work. And there are even others, but the one that I'm interested in right now is what's called potential energy, which is the energy that something has because of its position. The example we saw last fall is gravitational potential energy. An object is capable of doing work because of its position in a gravitational field. All of that water at the lip of Niagara Falls has a lot of gravitational potential energy. If instead of just letting it drop over the falls, if you run it through the hydro project instead, you can use that to generate electricity, which ends up doing some kind of work for somebody. So the higher you've got something, the more work it's capable of doing. A little waterfall that's only 2 feet tall could not produce nearly as much electrical energy as Niagara Falls does. So its position in a gravitational field makes it able to do work. And if you have a charge in an electric field, it's pretty much the same story. Where the charge is in that electric field determines how much work it could do, just like a mass in a gravitational field. So gravitational potential energy, electric potential energy. The stronger the field, the more work the charge could do, but the amount of work the charge can do depends not only on the strength of the field it's in, it depends on how strongly charged the object is also. A doubly charged ion can do twice as much work as a singly charged ion, all else being equal. And so the ratio, though, is something that's always the same. The potential energy per unit charge is a property of the field alone, and that's called electric potential. I guess we're all the way down here now. Slide it up. Kind of similar names, easy to get them mixed up, I suppose. Potential energy is measured in joules, like any other kind of energy. You chop off the word energy and just call it potential. That's joules per coulomb, energy per unit charge. As is often the case, this combination of units has a name of its own. A joule per coulomb is a volt, named after Alessandro Volta, who invented what we now call a battery in the late 1700s. I am not quite sure what happened to the letter A on the end of his name. I mean, Volta is not, it's not one of these names that's 27 syllables long. I'm not sure what was the issue with the A, but at some point somebody took it off. It's a volt instead of a volta. Many times, what's of interest is the difference in potential between 2 points. Actually, as the course goes on, I'll be talking about potential difference quite a bit more often than I talk about the absolute potential at some point. So same definition, just with deltas on it. Delta V equals delta potential energy over the charge, where delta means the difference. In this case, you've got 2 different points. Point number 1, point number 2, subtract V2 minus V1. That's the difference in potential between those 2 points. So I'm going to do one, and then you're going to do a similar one to kind of illustrate the idea of what this means. Find the energy delivered by each coulomb of charge from a 12 volt battery is what's under the hood of your car. I mean, you know, they call it, it's not exactly 12 volts, but that's what they call it anyhow. It's pretty close to 12 volts. So if, let's see, part A, if delta V is the difference in potential energy, the difference here in this case, by the way, would be the difference between the positive and the negative terminal of the battery, okay? If you turn on your headlights, electric charge flows out of the positive terminal of the battery, flows through the light bulb, back into the negative terminal of the battery, and then inside the battery, chemical reactions occur, which pump the charge back over to the positive terminal again, kind of like when you put the 2 different kinds of metal in the vinegar the other day. And if you leave it turned on for long enough, the charge goes around and around. The word circuit is a variation on the word circle. It just keeps going around. The energy being to pump it is being produced by the chemical reactions. So find the energy, it's delta PE that's being asked for. So take this definition and rearrange it. Multiply both sides by Q. One coulomb of charge would pass through a headlight bulb in, I don't know exactly what fraction of a second, but it wouldn't take very long. What that means, once again, is basically a certain number of electrons. Each electron carries a certain amount of charge. So you leave the bulb on long enough that that many electrons goes through it. Well, 12 times 1, hopefully you don't need it. Oh, you know what? A little less glare off the blackboard for the, Caitlin at least is in there watching us through the computer. So 12 times 1 is 12. As far as the units, a volt means a joule per coulomb. Joules per coulomb times coulombs gives you joules. And then repeat for, well, what I kind of had in mind when I wrote the question was house current. Cars are 12 volts, houses are 120 volts, except houses actually are alternating current, which gets a little more complicated. So we'll save that story for another day. I believe it's section 8 of this course where we talk a little bit about alternating currents. But to dodge that issue for now, let's say you had 120 volts of direct current, which you could get by, you walk into AutoZone and say, I want to buy all of your car battery. Actually, they probably have more car batteries than that. But if you get 10 batteries and hook them up in series, then you'd have about 120 volts of direct current. So similar to house current anyhow. Same calculation, except with a 0 on the end of the voltage. So if you've got 120 volts, the same exact number of electrons delivers 10 times as much energy to your light bulb or motor or whatever is running on this circuit. This is why if you take a light bulb that's designed to be used in your house, to keep it simple, let's make it an old-fashioned incandescent bulb. I mean, you try and hook up a compact fluorescent, for example, to a battery, and it's just not going to work. But if it's just a plain incandescent bulb with a filament in it, it's designed for 120 volts, you try and hook it up in a car, and you're going to get a lot of nothing. I mean, if you've got some sort of night vision goggles, you'll probably see a little infrared coming out of the thing. But as far as visible light, if there's any, it's not enough that you're going to notice it. If you take a light bulb that was designed to be used in a car and you hook it up to 120 volts in your house, it's going to give you a very bright flash. Yeah, you're just going to vaporize the filament in that bulb, just flash, and it's done, it's dead. Because the 120 volts put 10 times as much energy into that light bulb filament as it was meant for, which is just going to vaporize the metal. When it's designed for this, and you only give it that, it's 1/10 of the energy that's supposed to get there, and it's not going to make the bulb get very hot at all. So that's what the voltage means, the energy per unit charge. Comparing these two here, in part B, the same number of electrons delivers 10 times the energy. Incidentally, for anybody who's curious, this equipment that's sitting here is for a lab I have tomorrow morning. Just set it up ahead of time so they didn't have to come in at like 7 in the morning or something like that. Will probably happen again. Okay, let's see what's on the next. Oh, before we turn the page, a very similar question. The only difference is instead of it being a whole coulomb of charge, it's one electron. So you work on that for a moment. It shouldn't take too terribly long. And I'll go over that, then we'll turn the page. Same as before. Delta V equals change in potential energy per unit charge, rearranges into the energy equaling Q times delta V. Well, if you're gonna dot all the I's and cross all the T's, which is probably an obsolete expression now that everybody does things on a keyboard, but couldn't think of a better one. If you're going to dot all the I's and cross all the T's, 1.6 times 10 to the negative 19 coulombs gets a minus sign because electrons are negative. The potential difference is positive because everything is defined with positive charges in mind. A positive charge would go from plus to minus, kind of analogous to how if you drop a weight, it goes from a high to a low elevation. If you let go of a positive charge, it'll move from a high to a low potential, okay? So just like field lines point from high to low potential. I've already said last week, they go from plus to minus. So positive is the high voltage side. At least that's the conventional way of doing things. And so if the electron is going from minus to plus, its potential is increasing. So we've got a positive number for delta V. And negative 1.92 times 10 to the negative 8. I mean, it's not a lot of energy, but it's just one silly little electron. The minus sign because the potential energy the voltage increases as the electron moves from minus to plus, but its potential energy decreases because it's a negative charge. If it was a positive charge, when one increases, the other increases. But with negative charges, it's the opposite. Next page. This one doesn't actually ask you to calculate anything. This would be like one of those conceptual questions. In fact, I think that's where it came from. I think at one time this was a question I had on an exam in that last part where I put all the, the little 5-point conceptual questions. So think about that for a minute. In which case does the toast get darker? And after I've given you a moment to think about it, I'll talk about it. Anyone in the mood to share an opinion? No. Like, no, I don't want to look like a fool. You just go ahead and explain it. Okay. With 120 volts, that 1,000 coulombs of charge is going to deliver 10 times as much energy to the toast as it would if you plugged it into 12 volts, if you could rig up some way to do that in the first place. So yeah, your toast is going to be quite a bit browner with 120 volts because, you know, more energy is going to cook the toast more. Same amount of charge. Voltage is energy per unit charge. So more voltage would mean more energy. And then that next thing, I guess I already said a minute ago, electric field lines, which run plus to minus, point toward lower potential. They point from high to low. So the field vector E is one way to describe the strength of a field. The potential difference between 2 points is another way to describe the strength of the field. Since they're both kind of getting at the same thing, there must be some connection between them. And well, let's look at the case where you've got a uniform field because that makes the math easier. If you talk, for example, about the field around a point charge or a charged sphere, well, you know, the field is stronger when you're closer to it and the field is weaker when you're farther away. And so if you move a test charge from one point to the other, E is a constantly changing thing, and that's at least more sophisticated to deal with. I don't know if necessarily harder, but let's have a uniform field to talk about and leave it at that. And a good way of having a uniform field is that that's what you find between electrically charged parallel plates. Okay, you've got two, I'll swing that over there for a moment. You've got two metal plates. They're both seen here in cross section. Okay, you've got like one is here like this, the other one's there like that. And it'd be kind of like, if you want to make something like this at home, you get two pieces of aluminum foil and a piece of plastic wrap. And you put the aluminum foil on the bottom, the plastic wrap in the middle. That keeps the two pieces of foil from touching each other. And then the other piece of foil on top. And then you get some wires with, you know, alligator clips on them, and you hook them up to whatever voltage your battery is. What's going to happen is that, of course, you see, like charges I don't know why they call them like charges. They don't like each other at all. They want to get as far away from each other as they possibly can. So all over the negative terminal of that battery is a whole bunch of electrons. And when you touch that wire to the battery, some of the electrons say, you know, if I go out there in that piece of aluminum foil, I can get away from all these other jokers that are crowded around me here. And so some of them flow through the wire and accumulate on the plate that I got a bunch of minus signs next to. Every time an electron leaves the one terminal of the battery, an electron gets sucked into the other terminal of the battery, because that's kind of how batteries work. So the two plates have equal and opposite charges, plus Q and minus Q, and there will be an electric field pointing from plus to minus. Well, if you want to be exact about things, what I'm talking about here is infinite parallel plates. Well, that's kind of a mathematical abstraction. People talk about these sorts of things because it makes the math simpler, actually. But in realistic terms, what it means is that the point where you want to talk about the field is not too close to the edges. Okay, you've got this sheet of aluminum foil that's like 2 feet wide and 4 feet long on your kitchen table there. And it's separated by like 10 or 20 micrometers, however thick that plastic wrap is. So if you're talking about a point that's 2 or 3 inches from the edges are so far away compared to the distance to either one of the plates that for all practical purposes, it's infinite. So anyhow, this would not be true near the edges. Near the edges, the field lines start to bow outward and the field would be a little weaker than this. But if you're not close to the edges, the field is going to have the same strength and direction everywhere. And to get that number for the strength of the field, it's just the number of volts divided by how many meters are, well, at least in a vacuum, okay? Actually, when there's plastic wrap, things get a little more complicated. We'll talk about that in a minute. But for the electric field in the vacuum, it's just the volts divided by the meters. As it says in parentheses, if you play around with the units, it can be shown that newtons per coulomb, the unit that E is measured in, is equivalent to volts per meter. Okay, newtons per coulomb, volts per meter, same thing. So here's another one for you to work on for a minute. You've got a set of metal plates, just like I was talking about. You apply 800 volts, gives the separation. And by the time you get down to part B, you're calculating the force on an electron that's located between them. Maybe I should throw out a hint. Part A is just dropping numbers into the equation with the box around it there. For part B, go back to the definition of the electric field. E equals F over Q. If you know E from part A, and you know Q, because you can look up the charge on an electron, you can solve for the force. Number 4. Part A asks for the electric field. Electric field between a charged set of parallel plates is the voltage between those plates divided by the distance between those plates. In this case, that's 800 for the voltage, and it's 0.007 of a meter, 1.14 times 10 to the 5th. And you can label it volts per meter or newtons per coulomb, and it means exactly the same thing. I did volts per meter because I divided volts by meters. Part B. The force. How hard would an electron get pushed if placed in this field? This was a fairly commonplace, of course, this is all obsolete technology now. Well, not entirely, but for the most part. But in the old days, in a vacuum tube, you were frequently shooting a beam of electrons through some sort of an electric field that you were using to manipulate it. So force per unit charge rearranges into F equals QE, or EQ if you'd rather write it that way. You look up the charge of an electric. Now, I'm just interested in the size of the force. Okay, the question says how large. I'm just after the number of newtons. There isn't enough information given to figure out its direction if I wanted to. So the minus sign only matters if you're taking the direction of the force into account. The magnitude of a force, magnitude of any vector, is by definition a positive number. So that's why I'm overlooking the minus sign and just writing 1.6 times 10 to the negative 19 a coulomb with a charge, 1.602 if you want to carry it out further. 1.14 times 10 to the 5th newtons per coulomb times coulombs gives you newtons. 1.83 14. And the question doesn't ask for this, but if you stuck that force into F equals ma, the mass of an electron is only 9 times 10 to the negative 31. So even though that isn't much force, electrons are really, really lightweight. And that gives it just an enormous amount of acceleration. Like if you subjected a jet fighter pilot to that acceleration, you would kind of turn him into a yucky little puddle. But electrons are a lot more rugged than people are. Capacitors. Commonplace electronic device. If you open up a computer or a phone or a radio or something, you're going to find a bunch of capacitors in there, among other things. A capacitor is a device that stores electric charge. This might be the first time I've made an analogy between electricity and plumbing, but it certainly won't be the last. Electric current flowing through pipes is or electric current flowing through wires is a lot like water flowing through pipes. Okay, the wires are like pipes, a battery is like a pump, and so on and so on. A capacitor is like a tank. Okay, like if you've got a well at your house, if you live out in the country and don't have municipal water, you probably have a pressure tank in your basement. And in a circuit, that would be like a capacitor, okay? So it stores electric charge. The way you make one is exactly what I was talking about a few minutes ago, where you get the two pieces of aluminum foil and you put a piece of plastic wrap in between to prevent them from touching each other. A parallel plate capacitor is not the most common configuration because, you know, you want your phone to only be that big. And so what they do is instead of having something that takes up a big chunk of your kitchen table, you put some more plastic wrap on it for more insulation, and then you roll it up. So it takes up a lot less space that way. A lot of capacitors, when you look at them, are little cylindrical things, but that's what's inside of them, is a set of two conductors, one connected to each of the two little wires that sticks out of it. So just like I was describing, you hook it up to a battery and some electrons flow into one plate to get away from the other electrons on the negative terminal of the battery. An equal amount of positive charge collects on the other plate, and current flows until what's on the plates repels the charges in the wires as strongly as the battery does, and then the capacitor is fully charged. Unless, of course, you have some way to change the voltage. Now, if it's like one of our power supplies instead of a battery, where there's a knob, you can turn it up. Instead of having 1.5 volts, now you got 3 volts. Well, twice the voltage is going to shove twice as much charge into the capacitor. The amount of charge stored per volt is called the capacitance of this capacitor. C for capacitance, charge stored per volt, Q over delta V. Charge is measured in coulombs, voltage is measured in volts. Another combination of units given a name of its own. This is called a farad. I believe it's named after Michael Faraday. So this time they did away with a couple of letters on the end of the guy's name. I don't know why they did that either, but a 1 farad capacitor. 1 farad is a lot of capacitance. They exist. There are even bigger capacitors. I think there are like supercapacitors that they use in electric vehicles or something like that are like sometimes 10 or 20 farads. But yeah, you don't find those in the average TV set. In most applications, you're dealing with microfarads or even smaller. It takes some very clever technology to get larger amounts of charge stored in that. So C equals Q over V, that would be the general definition for any configuration, whether it's parallel plates or some other way of doing it. Textbooks talk about parallel plates a lot because, well, like I mentioned earlier, the math is easier, okay? You get fancier with the geometry, and you have to get fancier with the math that goes along with it. Between parallel plates, you've got a nice uniform electric field. So for the most part, that's kind of what we're going to stick with usually in this class. If it's a parallel plate capacitor, the capacitance is given by this formula at the bottom of the page. Epsilon with the 0 subscript, that's related to the Coulomb's law constant, actually. Coulomb's law, once again, was K times Q1, Q2 over R squared. That Coulomb's law constant is 1 over 4 pi times epsilon 0, okay? So that constant that appears in that equation there is the Coulomb's law constant. Well, it's the reciprocal of the Coulomb's law constant, and then you divide it by 4 pi, and that's equal to 8.85 times 10 to the negative 12. A is the area of the plates, how much of a square meter each individual one is. It's not total area of both of them, it's the area of each. D is the distance between them. The reason for the 0 subscript is that this assumes there is nothing between the plates, parallel plates in a vacuum. So 0 as in nothing between the plates. Well, we'll do a short example, and then I'll talk a little bit about what happens if you don't just have a vacuum. So there's a picture of the capacitor with various dimensions labeled on it, and you're supposed to calculate stuff. Part A. Well, to match the notation on the previous page, I'll call it C0, but you know, it's just the capacitance. The 0 subscript just emphasizes that there's nothing between the plates. Epsilon 0, A over D, because it's a parallel plate capacitor, that expression applies. You can look up epsilon 0, the permittivity constant, in the same table where you get the charge of the electron and all those things. About 8.85 times 10 to the negative 12. Area, well, it's a square. Area is the length times the width. The side of it squared is the area of a square. So 0.01 of a meter times 0.01 of a meter, and that's divided by 0.001, also known as a millimeter. So the capacitance is 8.85 times 10 to the negative 13th of a farad, which is a really small amount of capacitance, but as capacitors go, the plates are really far apart. on this one. You can kind of see from the formula, and other ways of arranging things, other geometries for the capacitor work the same way. It's an inverse proportion. The closer you get the plates, the bigger the capacitance. And there's ways of getting them a lot closer together than a whole millimeter. Part B asks for the charge on each if it's connected to 1,000 volts. Well, if C is equal to Q over V, charge stored per volt is capacitance. That rearranges into Q equals C times V. Capacitance is just the answer from part A. And 1,000 for the voltage. And we'll take our break here. If you're watching through the camera, I'm going to make the second half of the class a separate file.